Hi guys, I'm going to be doing number 5 on page 19 of the practice handouts, and this is much of the behavior of hemoglobin arises from the presence of salt bridges in the deoxytase form. One of the main salt bridge is that between the histidine imidazole group of histidine 146 and the carboxylate group of ASP 94, both on a B chain. Draw the salt bridge structural formulas as it might exist in the tense form. And so what this is this is aspartic acid, this is histidine, right? And we're going to want histidine to be positive and this to be negative. A salt bridge is between a positive and a negative ion in water or some other polar solution. And so even if you don't know where to draw your salt bridge, always do it from something that's negative and positive. So try and make your molecules somewhat negative and positive. Part B. If a mutant hemoglobin appeared with a lysine replacing histidine in position 146 of the B chain, what effect would it have on the following? Assume a pH of 7.0 if it is not otherwise given. Explain the reason behind your answer. So the way I did this is I kind of looked at what form is going to be in the highest presence in both the mutant and the wild type. The wild type being the one with histidine, the mutant the one being with lysine. So if we look at the pKa's between histidine and lysine, the pKa can be anywhere from 6.0 to 7.0 depending on where you get it from of histidine. So when we lose this H, I just wrote these as R groups so I didn't have to draw out the whole thing, but pretty much, you're losing this H and it's going away, and that's where the pKa is. Same thing over here for lysine plus neutral. So what this means is that this pH for, I'm going to draw a line here to separate the two. Sorry guys. Is that this is going to have half a positive form and half a neutral form, whereas this is going to be pretty much all positive. Remember when we were calculating net charge? This net charge would be around 50%. This net charge is 100%, or 1. This would be 0.5. So this plus charge is going to be a lot stronger, and it's going to attract this negative O a lot harder, stronger. So the strength of the salt bridge would increase. The oxygen binding curve of HB versus PO2. So I also like to always draw out this too. I always like to draw out an oxy to deoxy state. And when everything's going right, I'm here. Right? I'm always in the center. That's where life is. It's in the center. It's in equilibrium. Until some sort of mutation happens. Then we go either way. So your deoxy state is going to bind O2 less strongly. More strongly. Okay? So what that means is that when we have our forms and our main salt bridge is becoming stronger, that means it's going to favor our deoxy form. And so what that means is that it's going to bind O2 less strongly. So let's see if we can draw that. And this is the binding curve of hemoglobin, the amount that's bound percentage-wise to the partial pressure. So this is going to be our normal one. Now let's just pick some points here. Right? So if it binds oxygen less, that means that PO2 is going to have to be in higher concentration. Right? So in order to have this much saturation, we're probably going to have this much partial pressure. Same thing here. Same thing here. As we go up, we're going to okay. And so what does this mean? This is a mutant, by the way. And so what this means is that the bottoms and the tops are going to be exactly the same because we're not changing anything about what happens when oxygen is way too much or way too little. It mainly changes right here in the middle. That's where everything really makes the biggest difference. So like I said, what I like to do is I like to sit here and then say, okay, well the mutation is favoring something. The mutation is favoring salt bridges. It's making salt bridges stronger. Deoxyform likes salt bridges, so I'm going to go over this way. Binds O2 less strongly. If it made salt bridges weaker, I'd be going this way. And then the curve would be on the other side because it would bind O2 stronger. So it just really, the thing that I like to do when I'm doing these prompts, I like to write what each position likes the most. Deoxyform likes high concentrations H plus and CO2. Alright, stuff like that. Time for the final part here, which is kind of the trickiest one. So the Bohr effect in a shift of pH 7.0 to 7.2. So what you're looking at, this one's going to be really, really complicated for me to explain in a video without talking to you face to face, but I'm going to try my best. So the Bohr effect, by definition, is the effect of H plus on O2 binding. All right. Let's go back to our roadmap. Let's just give this 7.0. It's going to be close enough. All right. So raising our pH from 7.0 to 7.2 is going to have a huge effect from here to here. Right? Because you're going from here to here and you're significantly increasing this factor, which decreases the R plus form, right? What that means is that it's going to have your Bohr effect is very large. Because H plus and the increase of this pH is going to be very, very high. And this is when this is our wild type. This is when histidine 146 is there, not lysine. So our Bohr effect is very strong and very, very high. Okay. Now when we look at lysine, (7.0 to 7.2, or pH. This is lysine. This is R, right? The relative concentration of R plus isn't going to change very, very much at all. It's going to be basically 100% the whole time. So there's going to be very, very, very little effect of H plus on O2 binding. Alright, so what that means is that by this rationale, your Bohr effect decreases. Compared, because the histidine has a very, very huge Bohr effect. Where the lysine, when this pH changes, it has pretty much no Bohr effect at all. And so that's why in the answer your Bohr effect should be decreased. So this is very confusing. This very last one, it's very counterintuitive, but hopefully this part did help you guys out. Please send me any emails if you have any questions, and good luck on your midterms.